Welcome again. Today we will do interplanar spacing for the crystal structures. Very special topic for the orthogonal crystal system. Typically we are doing here orthogonal system. When we say, then we mean by the systems or the rather crystal structure systems in which all the angles are 90 degrees. All the interaxial angles are 90 degrees, right? And we know about that. They were the cubic, tetragonal, and the orthorhombic. Obviously, the orthorhombic case is the most general case where A, B, C are not equal, and other two cases are the special case of this orthorhombic. So, we will discuss everything from the point of view of orthorhombic crystals. So, interplanar spacing is sometimes called the separation between the lattice plane or lattice plane spacing, D spacing, and it is specific for the different I mean to say Miller indices HKL. So we denote it like DHKL, and that's why it is called some of the time D spacing. So you know that, let's say these are the planes, Miller planes you have, lattice planes you have with some Miller index HKL. So the perpendicular distance between these two is called the separation between lattice of the plane, interplanar spacing, or D spacing. Understand one more time. You know that there was a crystal and it has a plane, lattice plane like this. Arbitrary plane is this one. And you know it has the parallel set of planes. So between these two parallel planes, there is a gap, perpendicular gap like this one. And that gap is called D spacing. So this is the simple definition of the interplanar spacing. Now look at with the another plane. See this. All planes are parallel. The spacing between these will be simple, same as it should be, DHKL, denoted by DHKL. Right? Understandable? So now you can define interplanar spacing. The interplanar spacing denoted by DHKL is a perpendicular distance between the two adjacent planes which are parallel with the Miller indices of HKL. So you know about that? Now knowing the HKL value will be different in the different crystal structures. So of course it depends on the crystal structure. And typically if the crystal structure is not orthogonal, then it could be the different thing. So let us see how we come to arrive to calculate about this lattice spacing. So for that we require some understanding of reciprocal lattice. Very small. I will not do detail of the reciprocal lattice here. So you know about the orthogonal system, and we will talking about the only the orthorhombic case because this is the most general case. So we'll talk only about this, and we will generalize this and further specialize on the other two. So we know the real vector about that. So ABC, what could be the real space vector? Simple. AI along the x-axis, y-axis, and z-axis. So we have the component. We know that it has axis of ABC. So it's a ABC. So it's a real lattice vector. It's nothing about more serious thing. We know about the position vector, how to estimate. So similar to that, this is a real or primitive lattice vectors. Now what to do when we have this is the plane, let's say, and this is the plane. You know, this is the plane 1, 0, 0. So we have that's a in general case particular, and there is a space between that, and likewise we have parallel many planes. So this thing is called lattice spacing or the interplanar spacing between these two planes and denoted by DHKL. So these planes have a index, Miller indices. What could be the Miller index of this is H, K, and L. So let this be the Miller indices of this plane. Understandable? So we define a reciprocal lattice. It is just in the parallel way of Fourier. What you do, the how you do the reciprocate it. So reciprocal lattice. In the reciprocal lattice formation, it is generally defined in terms of H, K, L, with the reciprocal of A, B, C respectively along the axis. So it is 2 pi by A along the x-axis, 2 pi by B along the y-axis, and 2 pi by C along the z-axis, and further multiplied by their respective Miller indices. For example, H for x-axis, K for y-axis, and L for z-axis. So this becomes the reciprocal lattice vectors. So I will not go in the detail of the reciprocal lattice now. Right now, we will just do the, I want to say, the magnitude of that. And if you have a simple lattice, so you know what could be the magnitude of this thing. So a square, b square, and c square. So this is magnitude. The only thing that should know about that is that this magnitude of this reciprocal lattice vector is related to uh, spacing by this relation. So this is the important relation that you should know about that. Okay, so G of HKL, the magnitude of a reciprocal space lattice, will be equal to 2 pi upon of the spacing for the HKL Miller planes or lattice planes. So finally, when you substitute this, what you get? This thing. So you will know that the reciprocal of this will be given to this. So this is the general relation for the, I want to say, lattice spacing. When you say lattice spacing, that means you are talking about that 1 upon d square HKL equal to 1 upon h upon a square plus k upon b square plus l upon c square. So you know about the what is the formula for the spacing. So once you know the formula for the lattice spacing, we know how to define the interplanar spacing, and now we have the general formula for that. I mean to say d spacing in case of orthorhombic case. So we need not to do worry about the orthorhombic case, but in the tetragonal, you know that what's happened in tetragonal, there is A equal to B. So you can replace this by A, here B by A. So you get this thing, right? H square plus K square, and this is A square, this is A square, so LCM will be the same. So this is for the tetragonal. Well, in the cubic case, again here it will be again a, so everything is a, so you can take the LCM and a square will be going up, root of that will be a only, so a is here. So finally you got simple case for the cubic. It is dhkl equal to a upon h square plus k square plus l square. So that's a simple thing that you are getting here, right? So this is simple relation. So knowing this, let's me summarize for the orthogonal systems. For the cubic, we will tetragonal and the orthorhombic. We know about the orthorhombic, so we can drive it in the reverse way. So we know about the tetragonal. It's 1 upon d square equal to 1 upon h square plus k square upon a square plus l plus c whole square. So this is the formula for the tetragonal, and for the cubic, very simple. It's a lattice length upon the sum of square of sums of all Miller indices. So this is a simple case. Let's apply it on the some of the numerical cases where the more Miller indices is given to you. It is 110 and lattice constant is given. Answer you can have this by using this formula. If you're not getting get this relation, you can understand from here. If you're not understanding that, HKL is 110, so you can put it 110. So square of everything will be the same. So it will become just about of a, we know we have 4 upon 2, and what we don't have, this is again the root 2. So you know the dhkl, so calculate it. It is in term of angstrom, so in term of angstrom, so answer will be this one. So this is simple case for the d spacing. I hope you enjoy the this very particular video and learn that how to calculate the d spacing for a particular crystal system. Typically, they are orthogonal. Thanks for learning with YJES. So we will meet again. Till then, bye bye.